So, hello everyone. Good day. I know the memo states that we're supposed to have online synchronous meeting, but personally, I think that it's ironic how now that the typhoon, no, not typhoon, but tropical storm has become severe, so we're going to expect possible intermittent connection or perhaps, God forbid, an electricity interruption in some areas affected by the tropical storm. So I decided to record this video for our next topic. Supposed to be we are to have a quiz bee, and it's about the videos I have given to you as your not reading, viewing assignment for preparation of the supposed quiz bee. Sadly, we cannot have a quiz bee. So anyway, we have to move forward, but we can still have the quiz bee. At least you're already prepared to answer the questions once we can already meet face to face. So today we're going to start with nuclear chemistry. And among many branches of chemistry, this branch is quite a continuously evolving branch of chemistry because one, people in science continue to study about it. So we are still in the process of learning more about nucleus. So nuclear chemistry is concerned with changes in the nucleus of the atom. In fact, when I was in first year, that was way back, no, not first, 2018. So, that time, there were even new elements discovered. So, meaning, even in the field of chemistry, specifically nuclear, since when you discover new elements, so you study about its nature. And we always go back to the basic representation and the basic unit of elements, which is your atom. And your atoms contain nucleus. So, meaning, up to now, nuclear chemistry has no definite end, or it's still evolving. That's why it's quite new, and although it's straightforward, but its reality is quite complex. So if you notice, so when we talk about nuclear chemistry, it's always associated with disaster and lessons on safety. So nuclear chemistry is associated usually with this symbol. So this symbol is showing that that zone or certain area is radioactive. So in the lab, perhaps not here, but maybe in hospitals or labs having more complete equipment wherein there is radioactive substances found, so we might find the symbol. But in hospitals, we can actually find radioactive zones. So one of which will be medical imaging. So we have MRI, your CT scan, X-ray. So those are actually concerned with radioactive or nuclear chemistry. So in terms of disaster, so two famous incidents that involve compromised safety due to the complexity of radioactive substances would be Chernobyl incident in 1986. So none of us were born that time yet. And Fukushima Daiichi power plant incident. So I was probably in, well, elementary or high school that time. But to us, it seems okay, an accident happened. But to the people within that area, so it's already a massive disaster because, for one, even up to now, Chernobyl remains a no entry zone. No entry for residents, for commercial activity, and even people who can enter are limited or restricted. So even in Fukushima, so that zone near the power plant is no longer inhabited by residents. That's because of the effects of radiation. So that leads us to wonder why or what's with radiation or with radioactive substances or nuclear substances, particularly so nuclear fuel, that makes those incidents become a lesson. So in terms of fuel, so energy, we're concerned with energy. So there are trivial facts, not really trivia, but it's really economically well, more inclined to economics in terms of nuclear energy. So one reality or fact is that nuclear fuel is extremely energy dense, meaning if you have one pellet of uranium, which is usually used as fuel for most power plants or nuclear reactor, so that small pellet can actually be equivalent to these volumes or mass of other energy sources. Say for example, natural gas, so you have 17,000 cubic feet. So one uranium pellet can already produce as much as 17,000 cubic feet. Or you have 149 gallons of oil or 1 ton of coal. So these three below are conventional sources of energy which a lot of countries, so we all know a lot of countries are struggling to obtain or to produce. And if we have a nuclear facility, so imagine we only use one pellet of uranium. So that means we can save resources. However, handling nuclear substances is the challenge. So, capability of handling nuclear fuel or nuclear substances. So, capability to maintain nuclear facility. Because remember, the materials or equipment used to process uranium or nuclear fuel is different from those that we use in industry today. Okay? So that makes nuclear chemistry, aside from an evolving field, it's also a challenging field because it can tap on the economic capability of our country because, well, intellectually wise, we can always cope up. In fact, we already have nuclear related studies. So we already have nuclear organizations in the Philippines. But the question remains. So, will the people agree? Will the government consider? So, one thing for sure, time will tell. And remember that our country is really prone to weather disturbances or environmental concerns. So, that's also another thing to consider. So, can we what's our response in terms of incidents? So Chernobyl is in, I think it's in Russia. So it was the former United States of Soviet Russia. Am I correct? So USSR, um, Ukraine rather, uh, Soviet Republic, sorry, I had it wrong. So it is the Soviet Union, so Soviet Socialist Republic, but now it no longer exists. Then Fukushima, Japan. So these two countries actually are capable in terms of economics, but they even struggle at terms of response that time because of turmoil or conflict, diba? So how much more us, in which we have a lot of, well, drama going on in the government and in the social status of our country. So maybe in the future. maybe there are strong groups who can actually convince. So we already have power plants here in the Philippines which are nuclear, such as in Bataan, but it's not working because a lot of people still oppose. So majority are still in the opposition. And we can't force it because remember we are democratic republic. So still, economics, engineering is always tied with economics, government, so social responsibility. Always take note of that, future engineers. Okay? So much about the trends in nuclear chemistry or nuclear standing of nuclear fuel. So here, we are to go back to the basic unit of chemistry usually. When we think of elements, so we always go back to atoms. Okay, so each element in the periodic table, we find their different symbols. So here, let's just recall. So X here stands for your symbol for your element. A here is your, so this is usually your, it is always the value or figure shown in most periodic tables with decimals. But each element is designated their mass number. So, bati ng agi ni ma'am. So, A here is your mass number. Mass number is the sum of your protons and, so take note, protons and neutrons. Okay. So, protons is positively charged. Neutrons are no charge at all. Okay. So, always remember, take note that an element has the same number of protons and electrons. So, kung pila imong proton sa element, maura pod na ang number sa electron. Ang maglahi is your neutron. Okay? That's the common mistake a lot of people get. So, number of protons equals number of electrons. Okay? Now, here, below is Z. So, this is actually your atomic number. Okay? So, your atomic number represents the number of protons present in the element. Okay? So, why is it Z? So, it's actually in etymology. So, Z comes from Z. So, perhaps it's in German. So, Z meaning in German. So, it means number. Okay, so Z. So, number. Okay. Now, A for atomic mass, Z for atomic number. Okay. So, para dili confusing, so A for mass number, Z atomic number. Okay. So, X is symbol for your element. Okay. So, let's have an example. So, if you're going to look into your periodic table, so you'll find many there. Okay. So, let's just pick. So, say for example, so today is October 24. So, let's look for element number 24. Okay, so I hope you're also looking at a periodic table. So it's up to you what periodic table you're going to use, as long as you know, you can see the mass and the atomic number. So say for example, let's look for element number 24. From the periodic table, so number 24 is, symbol is Cr, which stands for chromium. Okay. So, chromium has the atomic number of 24. Oops. And the mass number is, so the atomic mass is in decimal usually. So, that's 51.9962. But so, rounding it up, so you have mass number of 52. Now, we know from this representation that 24 is the number of protons. So number of protons for chromium is 24. Now, how many neutrons are there? Okay, so what are we going to do to get the number of neutrons for chromium? Okay, so simply we are to subtract the mass number, subtract the number of protons from the mass number. So number of neutrons is, so mass number minus number of protons, which in this case, so for chromium, number of neutrons is, so 52 minus 24. So how much will that be? Okay, so how much? 52 minus 24, that's 28. Okay, meaning chromium has 28 neutrons. Now, how many electrons are there? Okay, how many electrons in chromium? So as I have stated, number of electrons equals number of protons. So meaning, if there are 24 protons in chromium, there are also 24 electrons in chromium. Okay? So really easy, right? So minus minus ra. Okay? So I hope you get the relationship between mass number, atomic number, and number of protons, number of neutrons, and number of electrons. Okay? So hopefully it's clear. Let's have another example. So let's use, let's say for example, so let's use uranium. Okay? So looking at your periodic table, uranium has a symbol, chemical element symbol of U. And the atomic number is 92. For mass number, so stable form, it is 238. Now, how many protons? So number of protons based on atomic number, we have 92. Number of electrons equal to the number of protons, this is also 92. Now let's count, or let's look for the number of neutrons. So that's going to be 238 minus 92. So meaning, how many neutrons are there? So we have, this is 23 minus 9. So this is bilangan class 1, 4. This is supposed to be 1, 4, 6. Okay, there. So meaning there are 146 neutrons in uranium 238, and you have 92 protons and electrons. Now, this leads us to the next important concept in nuclear chemistry, which is about isotopes. And from the video, you have learned the definition of isotopes. So isotopes are atoms of the same element which have the same number of, so may the same number of protons, or your atomic number, and what else? Unsa may lain sa isotopes? What is different? So isotopes have different mass number, or your A. Okay? So isotopes, the same number of protons, or the same number of atomic number, or the same number of electrons, but different mass number or atomic or A. So meaning, what else is different? Since different ang mass number, so maglain-lain pod ang neutrons, 'di ba? In comparison, so the neutrons will change depending on each isotope, but the same element. Okay, take note, same element. Okay? Now, one of the most common isotopes is actually hydrogen. Okay, so hydrogen has 3 known isotopes. So let's name each. So what is the symbol of hydrogen? Looking at your periodic table again, Sharo. So looking at your periodic table at the leftmost, so you have their hydrogen with the symbol of H. Okay. Now, the most common known isotope or the stable, which we all know, is hydrogen having 1 proton with mass number 1. This is the hydrogen we always encounter. So whenever we speak of hydrogen, so this is the isotope of hydrogen that we talk about. But it also has another isotope. So it is usually used to refer to heavy water. Okay? So when we think of heavy water, we always refer to the isotope of hydrogen. Still, it has the symbol H and the number of protons, 1. So atomic number 1. But since this isotope contains also 1 neutron, because take note, hydrogen has, so this hydrogen we know, 1 proton, no neutron. Okay? Meanwhile, this isotope has 1 proton and 1 neutron. Meaning, your mass number is now 2. Diba? Because 1 plus 1 equals 2. And we call this isotope your deuterium, which is usually associated with heavy water. Okay? So deuterium is found in heavy water. Okay? So meaning in heavy water, instead of hydrogen, so instead of this hydrogen in heavy water, that molecule in heavy water contains this hydrogen. Okay? So that's why when we write heavy water, we usually represent it as T2O. So this is heavy water. Okay? In comparison to the chemical formula of water, which we know, which is H2O. Okay? So I hope you see the difference. Okay? Now, these two are actually stable. Okay? So these two are stable, but then we still have another isotope of hydrogen. So this time, if we have, so where will I write this? So if we have the hydrogen, isotope of hydrogen having 1 proton and 2 neutrons, then how much is our mass number? Okay. So 1 plus 2, so we have 3. So we call this isotope as tritium. Okay. And among the three, tritium is unstable. So, uses of tritium include radioactive tracers. So, it is more of medical or scientific use. So, it is unstable, but it can still be used purposefully. Okay? So, these are the isotopes of hydrogen. So, we have deuterium, tritium, and hydrogen. Okay? Now, what are other common examples of isotopes which are famous? So, one of which will be carbon. Okay? So, if we look at the periodic table, so drag. So if we have here, so what is the symbol for carbon? So very, very easy, very, very common. So carbon, very famous, so we have C. Looking at the periodic table, what is the atomic number of carbon? So you're going to look at, you will find, so it is 12. Am I correct? Actually, no, bali. So 6 is the atomic number. Then 12 stands for the mass number. Okay? Now, this carbon is the stable form of carbon. So carbon 12 is usually, so may uses ni carbon 12. It is actually the most abundant, and it is one of the two stable isotopes of carbon. But this is more abundant, that's why it is more known. Okay? So it is found in a lot of substances or even in different naturally occurring organisms. So for us, we contain carbon. We are living. So when we have our different food, so food actually contain your biological macromolecules, meaning long chains of molecules. So you have your carbs, you have your lipids, you have your proteins. These three contain carbon. And this carbon is in the form of carbon 12. Okay? And these three are, when intake by your body, so it is broken down into building blocks. So you have so for carbohydrates, you have your sugars, your monosaccharides. For lipids, you have your fatty acids or triglycerides. And of course, for proteins, so you have your amino acids. So all these, in terms of structure, you have carbon 12. And even in nature, so you can find carbon. So, ma'am, activated carbon. So, yes, that is still carbon. But apart from this carbon, we have the common isotope, which is really interesting since it is involved in a scientific method that can determine the age of, say, artifacts or old things, even as far as about 60,000 years, perhaps. And that carbon is what we know as carbon, carbon 14. And this carbon, this isotope of carbon is used to conduct radiocarbon dating. Dating in a sense that it is determining the age of old artifacts or substances found. Okay? So, how many protons? So, let's assess each isotope. So, let's determine the number of protons, electrons, and neutrons. How many protons are found in carbon 12? So, we have 6. meaning we also have 6 electrons. And because we have a mass number of 12, so 12 minus 6, we have 6. Very easy. How about carbon 14? Okay, so carbon 14, so we have number of protons, we have 6. Number of electrons, still 6. 14 minus 6, so we have 8. So meaning there are 8 neutrons present in carbon 14, which is 2 more than carbon 12. Okay, so carbon 14 is usually used in radiocarbon dating. So it is determining the age of different artifacts or fossil fuels, whatever is being excavated, or even the ages of trees. So based on radiocarbon dating. Okay, so that's because radiocarbon for carbon 14, so it can transmutate, so undergo transmutation. Okay, so whatever amount of carbon 14 is left in a particular organism being under study, so that determines how old or how long that certain matter has been dead. Okay, so that's how carbon 14 is used. Okay, now in relation to isotopes, so we already understand how isotopes differ from each other. So this time, let's proceed to the different types of radioactive decay. Okay, so let's proceed to the different types of radioactive decay. So we know that nuclear energy is massive. Okay, so small, we're dealing with small, so we cannot see them in under the naked eye. So we cannot see nucleus, we cannot see atoms. But despite that, we can feel, or we can actually magnify their capacity in terms of their energy. And these energies, so your ionizing energy is either released through because of different types of decay, or these are your reactions involving your different radioactive substances or different elements in general. Okay, so there are different types of particles that we have to consider. So you have alpha particles. So here is a illustration of the different particles that can be emitted by a certain sample, usually radioactive. So first off, we have alpha, then we have beta and gamma. So alpha, if you look at this illustration or figure here, alpha particles cannot go through aluminum foil. Meanwhile, beta and gamma can penetrate the aluminum foil. What does this mean? So this means that beta and gamma is more penetrating, or can emit more energy than alpha particles. Okay. Now, there are different types of decay involving these particles. So we have, first is alpha decay. Okay. So alpha decay is the release of alpha particle equivalent to your helium. So you have helium particle. So looking at the periodic table again, so helium has an atomic number of 2 and a mass number of 4. So for example, so we have uranium. So uranium here is your nuclide. And this can actually undergo alpha decay or alpha emission. So decay is also termed as emission because you are emitting or releasing this certain particle. So alpha decay is the emission of alpha particle. So with that, what happens here is that initially you have So for uranium 238, you have 92 as your atomic number. So here, if your uranium 238 emits alpha, so you're emitting helium. So meaning you're going to determine what element is produced apart from helium. That's where our arithmetic skills and periodic table come in. So simply, to know the element being emitted apart from alpha particle, so this is your alpha particle, you have to look at, so you have to subtract, so balancing yapon ni siya class. You have to make sure the mass number at the right is balanced with the mass number at the left. The atomic number at the right is also balanced with the atomic number at the left. So, here, 92 minus 2, we get 90. 238 minus 4, we got 234. So, the technique here, class, is you simply look at first the atomic number. Okay? So, you have to notice the atomic number. Why? Because remember, the atomic number identifies the element. Okay? So, atomic number, okay, let me, atomic number identifies your element. Because when we look at the periodic table, we usually use the atomic number because for one, it is unique. Okay? So, atomic number identifies element. Okay? So, hopefully, so, matiman-an lang ha nga, atomic number identifies element. So, unaha og minus ang atomic number. Okay? So, hopefully, it's clear. So, let's have another example. Apart from uranium 238. Okay, dere. So, we know that this part here is alpha decay. So, let's focus here in this second. So, let's focus here first. So, let's focus here below first. Saan naman to? So, we know that this is alpha decay or alpha emission because of the presence of helium in the product side or alpha particle in the product side. So, let's determine what element is being released. So, first off, we have 90 minus 2. So, pila ng 90 minus 2? So, we have 88, diba? And when we look at your periodic table, let's look for element number 88. Okay? Okay, so ma'am, pangita daw ang periodic table. Okay, sige, go. So, element number 88. So, let's look for element number 88. So, let's open, so, periodic table. Then, we go to your elements, looking for 88. So, it is basically here, somewhere down. And if we look at, so, zoom in ta, what is element number 88? So, here, we have the symbol Ra, which stands for radium. So, element number 88 is radium. So, meaning, our product here is radium. Okay? So, element is radium. And then, our atomic number is 88. So, pila man ang mass number? 230 minus 4. So, we have 226. Okay? So, meaning here, this is radium 226. How about here above? So, you might say, ma'am, obvious because we're still talking about alpha decay. But in some problems, they will not tell you what is the what decay is your nuclide undergoing. Okay? So, also, here, since if your reactant is called your nuclide, so for alpha decay, if here, for example, thorium is your nuclide, Then radium here is considered daughter. Daughter. So it is the term to refer to, so one product of alpha emission. So the daughter nuclide or daughter. Okay, so here for polonium 210, so your daughter is sleeping with my husband. Kidding aside, so I don't know if you're familiar with that trend, but your daughter here is lead 206. Okay, now simply we are to subtract to know what is the particle being emitted. Okay, so here 84 minus 82, so we have 2. So 2 is the atomic number of our particle. Atomic number. Konohai. In terms of mass, so 210 minus 206, so we have 4. So meaning, the emitted particle here is alpha particle. Or you may also rewrite as, so this one. Same ra ng duha. Maura na sila. Okay? So very easy. Straightforward. Okay? So hopefully you get. Next will be, this time, if we're given the daughter and the particle, let's identify the parent. Let's identify the parent nuclide. Okay? So we are given lead as the daughter and alpha particle. So this time, since we are looking for the nuclide, we're going to add these two. So to determine the atomic number, we are to add. So 82 plus 2, we have 84. Okay? And looking at your periodic table, so let's go back. We have to look for element number 84. So looking at the periodic table, we have 84. So polonium. So meaning, so mura jud ni ganina class. 84, your element is polonium. 205 plus 4. So that's the time. So we're going to have some difference. So this is 209. Okay? So if we're going to compare from above, so this is polonium 209. Meanwhile, above, so sa may naa, we have polonium 210. Which means, we're already dealing with isotopes. Okay? So that's why we do not rely always on the periodic table in terms of filling out the mass number. Because we'll have to depend on the type of emission that your nuclide is undergoing. So the parent nuclide is undergoing alpha. So that's why, so we have 4 being subtracted from the mass number and 2 from your atomic number. Okay, so sayo na no? 1 plus 1, 2 plus 2. Okay, that's for alpha decay. This time, let's proceed to beta decay. So if you look at this equation here, or reaction, it's quite a lot. A lot is quite going on. But what's really the gist here is that you're emitting beta particle. So beta particle is represented by, so this one. This is your beta particle with a charge of -1. And we're going to apply that. So this particle here is your neutrino. Neutrino, kani nga beta particle is also known as neutrino. This here, symbol here, is written to somewhat balance in terms of concept. This one is your anti-neutrino. Okay? Now, that's because of the concept that, remember, an electron is not within the nucleus, diba? Remember, the electron simply surrounds your nucleus, but not really together with protons and electrons, and neutrons. So that's why this concept is introduced. Okay. So let's have examples. Okay, now, if we're going to consider, so let's try to answer first the one below. Because we're going to look for the, so again, daughter nuclide. So here, we're going to look at the atomic numbers. So here we have, so what is PA class? What is PA element? So try to recall. So PA stands for protactinium. So it's really not familiar, but it is radioactive. So protactinium 234. It has an atomic number of 91. Now, to get the atomic number, so what are we going to do? So we're not going to subtract. This time, we're going to add. Okay, you notice? So what's going to happen here? It's going to be, so mura na siya ginani, no? 91 minus negative 1. So what happens? We are adding 1, right? So 91 plus 1, it's 92. So go to your periodic table. So let me rewrite 92. Go to your periodic table, look for element number 92. So let's go to element number 92. So looking at here, so we have uranium. So we have uranium as our element. So symbol is letter U. This time, let's determine the atomic mass. Are we going to add or subtract? Answer there is no. Because remember, so here, in your neutrino, your beta particle, has a charge of negative 1, but you have 0 to add for your mass. So this will still remain as 234. Okay? 234. Uranium-234. Here above, so suppose we don't know what type of decay this is undergoing. So thorium-234. Assume we don't know what is the decay. So let's try to, so 91 here. And 91 is for your atomic number for the daughter, and 90 is for the parent. So what happened there is that, so we're going to subtract 90 minus 91. So what happens? So we have negative 1. Okay. So I hope it's clear, no? So here, our atomic numbers give negative 1. Then the same mass number. So the same, 234, 234. So meaning 0 above. So meaning this is a beta particle. Then we're going to add the antineutrino. Okay. So we're going to add the antineutrino symbol there. Okay. So that's how beta decay works. Now, let's have another example. So here, say for example, we have, so beta decay still. But this time, so what is this element? So 80 is your astatine. So looking at the periodic table, look at the atomic number of astatine. So astatine 218. So what could be the atomic number? So it's actually, so 85. Okay. But this is your product nuclide, or this is your daughter. So meaning this is at the right side of the equation. So what we're going to do, so this is right side. we're to determine the parent nuclide. But we know that this is beta decay. So what else is found at the product side will be your beta particle. So this is going to be plus your beta and your antineutrino. Okay? Now what we're going to do is, so we are to determine the atomic number of your parent nuclide or reactant nuclide. So we're going to add 85 and -1, right? So this is going to be, are we going to add? No, we're going to subtract. So 85 minus 1. So that's the time. So we can already have the identity. So 85 minus 1 is 84. Looking at the periodic table, what is element number 84? So looking at your periodic table, element number 84 is, so polonium. This is polonium. And for the atomic mass or the mass number, so you use the same as astatine. So it's 218 for this reaction. Okay? So do you see now the pattern? Hopefully you do, because we're going to proceed with gamma decay. This time, proceeding with gamma decay, so this is high energy. So it is known to have high energy. However, it is said to accompany only your other types of decay. So for example, the decay of carbon-14. So when carbon-14 undergoes gamma decay, so it can produce nitrogen-14, a beta particle, and gamma radiation. Okay, so take note, gamma, so no charge, so but it emits high energy, no mass, no charge, since it's considered electromagnetic. So gamma rays are electromagnetic radiation. Okay, so that's for gamma decay. Next would be electron capture. So by the definition, electron capture, so meaning your electron is found at the reactant site. So say for example, we have here aluminum 26. So still balancing class, when it is electron capture, you add, so electron here, you add this and you balance the charge. So take note, electron is -1, negative charge, so no mass. That's why you might have different atomic number but same mass. So it is to take note that you have zero change in mass for electron capture. Then still you have an accompanying particle here. So this is your neutrino. Okay, so if nagani dash sa baba, antineutrino, this one is neutrino. Okay, for electron capture. Then lastly, we have positron emission. So it is similar to beta decay, except that your products now are a positron and a neutrino. Okay, so ganina naman to'y beta particle and antineutrino. This time you have positron and neutrino. Okay, so it will have difference in atomic number but no change in mass. Okay, so balance na dyan siya. Okay, so let's have an example. So we are given these equations. We are to determine what type of decay. Okay, so let's look at letter A first. So we have oxygen 15 as your reactant nuclide or parent nuclide. And at the product side, we have nitrogen 15. So we have different atomic mass, the same atomic mass, different atomic numbers. So let's first see what is the difference of our atomic number. So looking at this example, so oxygen has 8 and 7. So meaning there is a change of 1, no? 1 for the atomic number, but 0 for the mass number. So what could be the product? So looking at the previous sa babaw, so we see that this is positron emission. Okay, so this is positron emission. So you have positron and neutrino. Now below we have, so obvious kayo, so we have beta decay. Okay, so looking at the atomic number, we have potassium 40, atomic number of 19, and a beta particle, so -1. So basically we'll have the same mass number. So ang atoa lang is the atomic number. So what happens here? So 19 plus 1, we have 20. What is element number 20? So I presume it's calcium. So element number 20 is calcium. So this is going to have symbol Ca. Okay, so this one here is calcium. Okay, next will be, so below, still potassium 40, but the unknown particle is at the reactant side. And looking at the atomic number at the product side, so we have argon 18, argon 40 with atomic number 18. So meaning there is 1 being subtracted from the atomic number of potassium. So this is -1. The same mass number, 0. Therefore, what particle is this? So we look above, this is electron capture. Okay, since we have an antineutrino. So let's double check. So electron capture. So yes. Are we, is this correct? So far, so let's see. Double check. So we got A right. Letter B. So correct. Letter C. So electron capture. Okay. So meaning this is correct. So we got it right. Okay. Then next we have, okay, so we have other examples below, but more or less it's the same as above. So for gamma, so it will only be shown. So for example, may gamma decay, so usually, so if you have equation B, naranay mo kuyog nga gamma particle. Okay, so let's try to summarize the different reactions. Okay, so let's try to summarize the different reactions. So for alpha decay, so we have, so your parent nuclide, so alpha decay here, so let's say parent nuclide, and then we have here mass number, atomic number, mass number, then product side, so alpha particle, so this is 4, this is 2 helium. Okay, so and then your new, so this is actually, so saan man pag-determine, so diba this is Z minus 2 and this is A minus 4. This is a different element. Okay, suppose X gyapon na. Okay, this is for alpha decay. How about for beta? Okay, for example, so still the same for beta decay, but what's emitted is your beta particle. So you have -1, 0. This one is beta, then plus antineutrino. So what happens here? So your daughter nuclide will have changes only in atomic number. So this is still A. Then for atomic number, so this is going to be Z plus 1. So see the difference? So that's for beta decay. Now, so this time, so we're going to have gamma decay. So for gamma, simply addition of symbol. So gamma decay usually denoted sa product side. So for gamma, usually add na siya sa product side. Okay? Next would be electron capture. So as the name suggests, so electron capture, so we have your electron at the reactant side. So your charge is so -1, no mass. This is electron. Then your product. So your product is, what is your product for electron capture? So suppose this is your daughter nuclide, and then you're going to have was that a neutrino or antineutrino? Let's review. So it's an antineutrino. Could be a neutrino, could be antineutrino. Then we're going to look at, so the atomic number. So there's a change. So this becomes Z minus 1. Then is there a change in atomic mass? So no. Okay. What else? So your positron emission. So what happens in positron emission? So going back, positron emission. So there is a product of positive charge. Okay? So instead of your negative beta, so you have +1. Okay? So here, let's look for an example of positron emission. So here, letter B, diba? Letter B is positron emission. Okay. I mean letter A rather. Letter A. So this is, say this is X, this is Z, this is atomic mass, then plus, is it a plus? So actually arrow sign na di ay. So your products, your positron emission, so it's going to be, so the same, no change in mass, but this is going to be, so what happens to your atomic number? So Z minus 1. Then what is the particle emitted? So that's going to be your positron. So this is going to be 1. Then no mass. Then of course neutrino. Okay, so this is positron emission. So you will be the one to label positron emission. So kamo na label ani no? Below is positron emission. This is electron capture. This one is, so if na gamma, i-add ra siya. This is beta decay. and this is alpha decay. So these are your types of decay. So pretty much straightforward and easy. So we have alpha, beta, so then gamma, and electron capture, positron emission. Okay, so hopefully you grasp the topic, and see you next meeting.